Howdy, welcome to Computer Graphics, Animation, and Simulation. In this video, we're going to talk about lattice Boltzmann methods. In particular, we want to talk about three main ideas. The first one is the algorithm itself, what lattices are, and then take a look at a very simple one called a lattice gas automata that LBM methods are derived from, ultimately. Now, lattice Boltzmann methods are an interesting way of doing fluid simulation. Because, for one, they aren't focused on solving the Navier-Stokes equations, and they use a very simple, very parallel process to solve the idea of fluid simulation by modeling collisions. So let's take a look at the algorithm. So the lattice Boltzmann methods essentially consist of two different steps. The first step is called the collision step, and the next one is called the streaming step. The collision step is designed to determine what happens when two particles collide. Now this happens on a discrete mesh that we then use rules for to determine what happens. So for example, if we have two particles colliding, then we might develop a rule which we might call an operator, and sometimes this is combined with a relaxation term. So in these set of equations, just for way of example, we have the Bhatnagar-Gross-Crook BGK term. And the idea for this one is that it helps to make the simulations more efficient, and we can go ahead and determine, the average result of several particles interacting inside of a lattice cell. Now, once we've determined what happens with the collision, then we want to cause the particles to begin propagating. We call this the streaming step. And this is basically simulating the movement of particles on the lattice. So the collision step is basically a rule set that determines what happens when particles collide inside of a lattice cell, and the streaming step decides how particles will then move throughout the system. In order to do this, we go ahead and we alternate these steps. So first we do the collision, then we decide the streaming, then we do the collision, then we decide the streaming. And while we're doing this process, it's very important for us to obey the laws of physics in terms of conserving mass, momentum, energy. So, for example, if we're conserving mass, we'd make sure that all the particles are preserved. They don't just disappear. So as they're propagating through the lattice, they maintain their state. Secondly, momentum and energy. The idea here is that if you're going to have two particles collide and then they start moving slower through the system, then obviously you want to make sure that you don't have a loss of energy there. Let's take a look at what a lattice is. So a lattice is basically a discrete grid of cells, and we're going to treat these cells like a cellular automata in terms of every single cell has a specific rule that we are going to use. Now, a square grid is a popular way of doing it, but it doesn't have to be a square grid. We could also talk about a hexagon grid, or we could talk about a cube grid. So if you want to extend this to 3 dimensions, in either case, you have to decide how the system is going to behave in this particular manner. Now, along with the lattice, you have to determine how are you going to represent the particles. And there's a variety of ways of doing this. It can go as simple as saying you have a Boolean particle. In other words, it's on or off. And or it could be some kind of continuous function where you're trying to represent the average behavior that's happening inside of that cell. And so determining, depends on how you decide you're going to actually implement this, but essentially just have a function that will take as an input one cell and its neighboring cells, and then you perform those collision and streaming operations on it. Let's go ahead and take a look at an earlier example, which is called a lattice gas automata, and see a little bit how this works. So one of the most popular lattice gas automatas that has been studied over the years is the Hardy, Pomeau, and de Pazzi automata, or HPP for short, and this is work done in 1973 and 1976. And the way that they did this was they created a 2D model, so these a two-dimensional lattice, and the rule set was very simple. So you have particles moving through the system, and they essentially can move in up, down, left, or right. So the first one, if the particles, as they're entering a cell, if they are going opposite each other, in other words, they're going head on, then they'll turn 90 degrees. So if you have two particles inside the cell, they're going against the same direction, then they will just simply change direction and start heading the opposite direction. Otherwise, they're just left alone. So in other words, if you have two particles coming in at right angles, then they just end up passing each other. So the macroscopic view of what happens is that you start to see wave patterns show up as the particles collide with the sides of the walls, or with the ends of the walls, where they just simply flip direction. And you can get, I guess, more advanced behavior like vortices and so on, but they are square vortices, which is kind of interesting. But this is a very simple model that you can kind of explore and play around with. So I just want to just quickly wrap up. We took a short look at lattice Boltzmann methods, talked about the algorithm. We have a collision step and a streaming step. We model these particles on a lattice, like a two-dimensional lattice or a 3D grid. And then the next thing we do is we looked at was a simple HPP lattice gas automata, which was a precursor to the current lattice Boltzmann methods. And this is something that's easy to experiment, especially if you already like playing around with cellular automata, and an interesting way of creating fluid simulations. So I'd like to thank you and just say adios.